Hi, my name is Mark Wilde. Thanks for listening to my talk. I'm going to talk about something I came up with called coherent quantum channel discrimination. I'm at Louisiana State University in Baton Rouge. This is a paper I posted to the archive back in January before the submission deadline for ISIT. Okay, so let's give some motivation behind this work. We're going to start with some background, and especially on diamond distance. This is a fundamental metric used to characterize distinguishability of quantum channels. Finds application in quantum Shannon theory, quantum computation, quantum complexity theory, etc. Why is it important? One reason is that it appears in the expression for the optimal success probability when you're trying to distinguish two quantum channels in a setting of channel discrimination called the symmetric setting. In this work, the main idea is to have a fully coherent version of channel discrimination where we take each of the steps involved and make them fully quantum such that everything is done in superposition. So you look at this, you might wonder, well, why would we be interested in this? There's at least two reasons. One is in the setting of quantum computing. Ideal quantum computers, they work in a fully coherent setting. And what we often do is take a circuit and promote it to a controlled circuit. For example, we take a NOT gate and promote it to a controlled NOT. And when we're constructing circuits, we may not make them perfectly. And so we may not make a perfect controlled version. And so we'd like to understand how the unideal case deviates from the ideal case, even when the channels are being used in superposition. So this can be helpful for that. Another possible motivation is recently there's been work on re-examining quantum Shannon theory if there's superpositions of causal orders. And so this error metric that arises from coherent quantum channel discrimination could be relevant there. Okay, so let's do a brief overview of diamond distance. It quantifies the distance between two quantum channels, and I know of at least two good reasons for using it. It's defined like this. It's a supremum over the trace distance of the states that can be realized by sending an input to the channels. The optimization is overall bipartite states with unbounded reference system, but you can show using some techniques of mathematics and quantum information that we can restrict the optimization to pure bipartite states where the system R is isomorphic to system A, the channel input system A. Okay, so what's the first reason why diamond distance is important? I'm saying it characterizes observational error between two quantum channels. So what do I mean by that? Let's say that the first channel, N0, is the ideal channel we'd like to implement, and N1 is what we actually implement. Then we can process a channel to obtain classical data by the following procedure. We prepare a state, a bipartite state, we send A through the channel, and then we perform measurement on systems R and B. So this is how we extract classical data from a quantum channel. And then when we do so, the probability to obtain a particular measurement outcome is given by this expression. Rho RA is a density operator, N0 is the channel. In this case, we said it's the ideal channel. And then lambda is a measurement operator. Okay, and so then the observational error between the deviation between the ideal case and the unideal case is this. So you take the two probabilities that you'd observe and take the absolute value. And then we want to figure out the maximum observational error, because that would be a function exclusively of the channels. And then what we can show is that this maximum observational error is the normalized diamond distance. You normalize by a factor of 1/2, and that gets you a number between 0 and 1. And so then the error lies between 0 and 1. Okay, what is reason number 2 to use diamond distance? It arises in an expression for the optimal success probability. So it's a slightly different scenario, an interpretation for diamond distance. The scenario is this. Alice prepares a bipartite state, similar to what we were talking about previously. She sends system A to Bob, who then randomly selects which channel he's going to apply. So he flips a fair coin, and he applies N0 if he gets the outcome heads, and N1 if the outcome is tails. He then sends the output of the channel back to Alice, who performs a measurement to decide which channel Bob performed. And we can say that she wins this game, meaning that she can distinguish the channels if there's a match between the choice of the channel that Bob selected and the decision that she made on which channel it is. So there's a probability of success for her to win this game, and that optimal success probability you can show, it's equal to this expression. So if the diamond distance is 0, the optimal success probability is 1/2, which is no better than random guessing. If the diamond distance is 2, this expression will work out to 1, which means you can distinguish the channels perfectly, and the channels are actually orthogonal. Okay, so let's review a bit some idea from quantum information that every quantum channel can be purified. Just like we can purify states, we can purify channels. What does that mean? The channel can be realized by tensoring in an auxiliary system in the state 0, applying an isometric channel, and then tracing over E. And so using this concept, we can give a different depiction of quantum channel discrimination. Now I'm calling Alice the prover, and I'm calling Bob the verifier. Okay, and that's language from quantum complexity theory. And so the game is the same, except I'm depicting a more fully quantum depiction of it. So I'm representing the random choice of the channel as a maximum mixed state. So that corresponds to Bob, or the verifier selection. Then there's a controlled unitary. This unitary or isometry is the one that's the isometric extension of the channel. The verifier sends this back to the prover, Alice, who then does a general unitary and sends back a decision as a single bit, which then Bob compares with his decision, his original selection, and he declares that Alice wins if there's a match. Okay, so what is coherent quantum channel discrimination? What I'm doing is I'm taking the previous picture and I'm looking at the incoherent parts and I'm making it coherent. What are the incoherent parts? Well, this maximum mixed state, I'm going to turn into a plus state, and the final measurement, I'm going to make be a Bell measurement instead, okay? And then I'm also going to allow for an uncomputing step, and that's so that the interactive proof system isn't trivial. So the new circuit looks like this. So we've replaced the maximum mixed state with a plus state. Alice is still taking an action with the end goal of maximizing the acceptance probability. And then here is an uncomputation step. And if you think about it in terms of simple examples, where if the channel is the identity or the NOT gate, you can convince yourself that this uncomputing step is sensible and necessary. That's done in the paper. I'm not going to do it here. Okay, so that's the idea behind coherent quantum channel discrimination. That's the picture. And I'm going to give you a little, we're going to step through it to give you a sense of the state at each step. Okay, so here's going to be step 1, step 2, step 3, step 4. And then I think there's even a step 5, which is the measurement probability at the end. Okay, so the initial state is this, plus and psi are A. This is what the verifier is prepared. This is what the prover is prepared. And then the prover sends A to the verifier, who does a controlled unitary corresponding to, controlled based on the value in register R1. And this is like this is the coherent version of the random application of the channel and conventional channel discrimination. Then Alice performs, the prover performs a unitary with the goal of optimizing the acceptance probability, with the goal of maximizing the acceptance probability. Then there's the uncomputation step. This is the state after the uncomputation step. And then finally, the measurement. I said it's a Bell measurement, but also we have a projection onto this auxiliary system that was used to make the channel. Okay, so the verifier performs this measurement and accepts if the first outcome occurs. What's the probability of success? You look at the state in step 4, you calculate the overlap, Euclidean norm squared, and this factor of 1/√2 I pulled to the outside. So that's the probability of success if there's a particular strategy of the prover. So then we optimize over all strategies of the prover. And one of the theorems in the paper is that the maximum success probability of coherent channel discrimination can be written like this, in terms of an infinity norm and using the notion of channel adjoint. So this is the adjoint with respect to the Hilbert-Schmidt inner product. It's a common concept used in quantum information. And it's like there's an optimization over measurements in the sense that these operators, when you square them, have to sum to the identity. And then we also have to allow for this environment system as well. Okay, it's interesting to compare this expression to the expression that we have for the success probability in conventional channel discrimination. This is another way of writing it in terms of what we could call the Heisenberg picture. And so then you see it, this one kind of looks like summing probability amplitudes, taking the opposite value and squaring them. So more like a coherent thing that we do in quantum mechanics is where this looks more like an incoherent thing where you're summing probabilities. The supremum should be over a P over M. So indeed, these operators sum to identity also. And so that you can start getting a bit of a feel for it by looking at that. Okay, so there are certain properties of this optimal success probability. That's what the paper gets into. Lower bound is 1/2, upper bound is 1. Upper bound being 1 is kind of trivial because it's a probability. I've proved in the paper that the upper bound is saturated if and only if the channels are orthogonal. So if and only if they're perfectly distinguishable. That's the only way you can win this game. The lower bound is saturated if the channels are identical. I was not able to figure out if we get an if and only if for the lower bound. So that's one of the open questions, and I'll return to it at the end. I was also able to figure out bounds relating the optimal success probability in the coherent version of channel discrimination versus the conventional one. So we have these relations. The coherent success probability is never larger than the incoherent or conventional one, simply because it's kind of intuitively harder to win this game because everything's operated in superposition. But then what's interesting is that it's possible to obtain an upper bound in terms of the square root of the success probability. So that's a nice relation between them. Another thing is to understand the sense in which this optimal success probability is a monotone, under which operations is it non-increasing. And this is something we do often in quantum information to understand things better. And so in this context, this optimal success probability is a monotone under the action of a superchannel. So I'm going to describe that concept for a little bit. So a superchannel is a physical evolution of a quantum channel. It accepts as input a quantum channel and outputs a quantum channel. So often it's written as theta. It accepts a quantum channel going from A to B and outputs a channel going from C to D. One of the fundamental theorems of superchannel is that it has a physical realization in terms of a pre and post processing. So if we plug in a channel to a superchannel, and we can then write things in a circuit diagram like this, where there's a pre-processing, there's a quantum memory system that gets passed along to the post-processing, and you draw a box around the whole thing that makes a new channel. Okay, so the main thing is that one of the main things about this monotonicity is that it does not, the optimal success probability does not increase under the action of a superchannel. And what is the idea behind the proof? Well, it's kind of like if you're trying to distinguish channels that have been processed by its superchannel, you can think of the pre-processing and the post-processing as part of the strategy being used to distinguish the two original channels in superposition. And so you adopt that mindset and you work a bit and you arrive at a proof. We use similar ideas for monotonicity of diamond distance under superchannels. Another thing that I'll just show here, I don't have time to go in detail, it's that the optimal success probability can be computed by a semi-definite program. So that's interesting and useful in a variety of ways, one of which is that we can understand it and compute it for example channels if they're not too large. How did this come about? Well, the protocol of coherent quantum channel discrimination is a particular kind of quantum interactive proof, which is a notion in quantum complexity theory that has existed for a long time. And it's known that every quantum interactive proof can be written as a semi-definite program. So you look at papers of John Watrous and Kitaev, and you put some things together, and then you arrive at this conclusion. Okay, so then we can use that to compare incoherent and coherent channel discrimination, their optimal success probabilities. So what I'm doing here is I'm looking at two generalized amplitude damping channels, one having a damping parameter 0.2, another having a damping parameter of 0.3. And I'm looking at how the distinguishability or the optimal success probability in distinguishing them changes as a function of the noise parameter. So as the noise increases, the success probability goes down. And then we see that there's a interesting gap between what can be done with coherent channel discrimination and what can be done with incoherent or conventional channel discrimination. Okay, so the concluding slide, what I've done in this work is I've defined a new task called coherent quantum channel discrimination, and motivated in two ways. One was in the context of quantum computation and controlled circuits. Another is as its possible use as a metric for quantum Shannon theory with superposition of causal orders. We found an expression for the optimal success probability, compared it to conventional channel discrimination, showed it doesn't increase under superchannels, and that we can compute it by an STP. The main open question is to figure out if the optimal success probability is faithful. So is that lower bound saturated if and only if the channels are identical. Thank you, Matt, very much for your time, and I hope to see you at next year's ISIT.